Welcome to our first set of notes in this class. When I start off notes, I will always start with a CLO. And the CLO, it stands for Content Language Objective. So this is our goal for the lesson. It's basically what you're going to learn. So this stands for students will be able to solve in writing a system of equations using graphing in the following language. If-then statements, y-intercept, slope, and intercept. So these are the vocabulary words we're going to learn, and you're going to use if-then statements eventually to explain what you learned at the end of the lesson. But in your own words, if you could guess, what do you think you're going to do during the lesson? So before I can begin to explain how to solve a system of equations with graphing, because this is the gist of what we're doing, since this is the very first lesson of a whole new class, I'm going to have to do some explaining of things you should have learned when you took the first half of this class. However, just because you quote unquote should have learned it doesn't mean you did, and it doesn't mean that you remember even if you did. So just to make sure that you know everything you need to know in order to do this lesson well, I'm going to do some notes on math in general so that you can do well on this lesson. Feel free to copy this stuff down if you don't know, if you didn't know it before I explained it, so that you have notes on it. But if you know what you're doing, you don't have to write this down. You can just watch. So when we do math, there are major competencies that the district identified that you need to know how to do really, really well in order to graduate. And the thing about them is they show up again and again in a lot of ways. So rewriting expressions is one of the major competencies. It's really easy to do on a simple level. So rewriting expressions just means I'm going to take something and I'm going to rewrite it in a way that's still entirely the same thing. For example, if I have 100, I didn't have to write it like 100. I could have wrote 10 plus 90 if I wanted to, because it's the same thing. So this and this are the same thing. And I only know that because I know add means to put together and go up, and 10 plus 90 more is equal to 100. So doing basic arithmetic falls under rewriting expressions because they mean the same thing. I could have also written this as 102 minus 2. I could also have said 100 is the same thing as 10 squared. And 10 squared just means 10 times 10. Also, other things, if I want to do multiplying things that multiply to 100, I could do 2 times 50. Don't forget that parentheses with nothing in between them means I'm multiplying. So parenthesis 10 with parenthesis 10 means 10 times 10. I don't have to put a parenthesis around one of them. So like I could have done it like this without the first one having a parenthesis. It still means 10 times 10. I could do it where the second one doesn't have the parenthesis. This still means 2 times 50. Because if there's nothing between the number and the parentheses, it means to multiply them. Another way to write 100, to rewrite 100, is I could do 300 divided by 3, because that's still 100. I could probably come up with hundreds upon millions of ways to rewrite the number 100. So right here I have 1, 2, 3, 4, 5, 6 different ways that you can write 100. Go ahead and give me a 7th way to write 100, to rewrite that. So this is very simple because the thing I started with was just 100. But in math, it's not the only type of expressions you have to rewrite. A lot of your math classes are teaching you new mathematical rules and what they mean, and new ways to rewrite the same thing, just make it look different. So we end up doing that a lot in math because the way it looks, we can do different tools if we can like make the math look different. So you're often asked to take equations or expressions and rewrite them in equivalent ways by following some math rules. So that's one of the major competencies that we have to do. However, all of those equations we give you to rewrite, like for example, I might be able to give you 3x minus 4, and I could write that in many different ways, following different rules. But all of these equations that we make in math, they all exist because in real life, every single thing in the world has an equation to it. Like if I wanted to make a skate ramp, I might use an equation like this because it kind of makes that shape, like that U-y shape. And in real life, everything that exists, the trees, the clouds, the buildings, they can all be made from equations. Every single part has its own equation to it. And everything in your life also could be represented with a mathematical equation, which is why the next competency that really matters is multiple representations, because equations are one way to represent a situation. So any situation in the world can be represented with math somehow. This one says I make $15 an hour and they take 25% of my paycheck and my taxes. This is true for most people. Most people lose 25% of their paycheck. And so if I wanted to write an equation about this, so when you make equations, you're going to need your x and your y, and you always have to figure out what each one is in the situation. Y is usually our amounts that we end up with. So right now, we're talking about how much money I make at my job. So it'd be like the amount of money I have. And the thing about Y is it's dependent. So depend means to rely upon. So the amount of money I have depends on how much time, how many hours I've worked. So X usually is time, not always, but it's usually time. It's independent because time goes by. Like it's just going to keep going. It doesn't depend on how much money you've made. Like time is going to go by whether or not you're making money. But the amount of money you have definitely depends on how much you've worked, how many hours you've worked. So in general, X can represent time and Y represents amount when it comes to real life situations. So when I try to make an equation for this, it always starts with Y equals, because the amount of money I end up with is going to depend on, it's going to equal $15 per an hour. But I don't know how many hours I've worked. So if I've worked 5 hours, I times that to 5. If I worked 10 hours, I times it to 10. And if I don't know how many hours I have worked, that's why I put times X. Because it's $15 times however many hours have gone by. Now, here's an interesting thing. I could write it like this with the parentheses. But if I just wrote 15X without the parentheses, it still means 15 times X. Like if this was your equation, and I said you worked for 10 hours, you would plug 10 into X by changing X into a parenthesis and putting the 10 there. So it's like there's always this invisible parenthesis around the X, but that takes longer to write than just 15X. So usually people go with 15X to say 15 times the X, how much time we've worked. However, you're not just going to make that money and take it home because they're going to take away part of your paycheck. So you take it and you're going to times it by the fact that your whole 100% of your paycheck is getting minused by 25% of your paycheck because they're taking part of it away. And if you do 100 minus 25, you're still left with 75% of your paycheck at the end of taxes. So really, you're multiplying it to 75% to figure out what's 75% of that. However, in math, you're not allowed to multiply to percents. You have to change it to a decimal. So to change it to a decimal, you divide it by 100, and it will become 0.75. That's also how you'd write 75 cents is like 0.75. So like you can turn percents into decimals by thinking like money. If I had 75 cents, it would be written as 0.75. So now this is my equation for this situation. Equations always have the x and the y in it. It's not an equation anymore. Once I say to you, how much money, if I said, how much money do I have after 40 hours? I would take my equation. And 40 hours is my time that I've worked. So instead of x, I replace it with parentheses 40. I'm plugging in 40 hours. And then I do the math to get the answer. So if I get $15 an hour and I times it to the 40 hours I worked, that would be 600, but I don't get to keep it all because the government takes 25%. So I'm only left with my 75%. I'm only taking home $450. So I could plug in 40 here for my x, but I could also plug in tons of other hours. I could say, well, what about after no hours? Well, after no hours, I have no money. So this is where tables get involved, because I can say, well, my x is that after no hours, I have no money. But I could plug in like a 1, and then I get out $11.25. So after 1 hour, I have $11.25. I could also plug in 2 hours. So at 2 hours, I have $22.50 because 0.5 means 50 because you could add a 0 at the end. And I could keep going. If I zoom out, you can see these points that if I connected them with more decimals, like if I plugged in, instead of just 1 and 2, if I plugged in 1.1, 1.1 would be $12.37. And then there's like a closer dot right here. And if I got a bunch of really close dots, it would almost look like a straight line, which is why when you replace this with an X, you see it's going to go through all those dots. And when you make a graph is all of the little like points in the table put together, because you're not going to list millions and millions of points. Like, why would I list this one here? At 0.85 hours, I'd have $9.56. Versus at 0.856 hours, I have $9.63. And I could figure out for every single second how much money I'd have. And all of those points together would make up this line. Now in math, it takes way too long to do all of that work. So typically, we just put a couple points and connect them. But there's all the invisible points in between them that represent, like this point right here represents after 1.68 hours, because my situation is about hours, I have $18.979 in my account, because that's why there's always an X and a Y. X is how much time has passed, and Y is the amount that you have at that given time. So then when you look at a graph, like if someone were to give me this graph, I would know very quickly, oh, you started with no money and then went up over time, because you always read your graph from left to right. And so you can see what's happening over time as you move over time, because it's moving up. So your amount's going up. Versus if this was negative in front. Now, if I looked at this graph, I'd be like, look, you started at $0 and then over time it's going down and you're losing money. So equations are best to use when you want to figure out any amount of time. Like, for example, after 1,000 hours, how much money would I have? Because you can just plug something into the equation and solve and get your answer. Tables are nice because it records your points very pretty, like in a pretty little style, and it's easier to graph from tables usually, but they don't usually tell you the whole picture. You only get a little bit of information from tables. When you put it into a graph and make a graph, the information you get is you can see what's happening over time pretty easily because there's a picture to go around with it. So once you get used to looking at graphs, you can look at them and be like, oh yes, this is what's going on, even if you don't know the equation or the table. But at the end of the day, those are our 4 representations. But at the end of the day, these are the 4 representations they want you to go back and forth between. If I give you a situation, so situation's the first one. Like this one up here, this was the situation. if you have a situation, you should be able to make an equation and a table and a graph from it. However, there are hundreds of types of equations in this world. In the first half of this class, you should have learned about linears, which make straight lines like this one did. So a linear, it looks something like y equals slope x plus your starting amount. And they grow in a very straight fashion. So they use linear equations to make books and tables and anything that has a straight line. It also represents situations where you're adding the same amount after each hour. Like here, after each hour, I'm getting 3 more per, if it's an hour, a day, whatever the time is, it's being 3 more each time, which means you're adding the same amount each time, which makes it look like a straight line. The other types of equations you've learned about were exponentials, where x is in the exponent like that. And these look more curvy, like the green line that just appeared. So it starts and kind of curves up. And so it makes a different shape. They use these a lot for like, if they're calculating anything that has curves in them that shoot up really, really fast, but only on one side. Because curves on both sides, it looks like this. You see how it's curving on both sides of the graph? There are other types of equations that kind of make weirder shapes, like this more like SE shape. There's equations for circles, there are equations, basically everything in the world you see, there's an equation for it. In the same way, any situation you have in your real life, there is a type of equation for that situation as well. And so a big part of learning math in high school is being taught all the different types of equations that exist and learn what situations do they represent versus what kind of graphs do they make and what picture do they make. And so you start to learn about all of them, and they want you to be able to go between the equation, the situation, the table, and the graph. So that's one of the competencies that you have to prove mastery on for all the types of equations. So it's like for linears, you already did that in semester 1. For exponentials, you already did that in semester 1 as well. But there will be many more types of equations you're going to learn about throughout the rest of your math that you're going to be expected to go between all of the representations on them. So that's this one here. Then another thing they expect you to be able to do with all of it is that once you have the graphs, you can start pulling out key features. So key features might be, for example, your starting amount, how much you start with. Or another key feature is your growth, like how are you growing by? Are you going up? Are you going down? Is it being added on? Is it being multiplied on? It's like, what type of growth do you have? We can also compare like the maximum and minimums. So maximums and minimums are like, where is the graph at the biggest amount or the smallest amount? So that's something else that you can compare within situations and graphs and stuff. And they want you to not only be able to find these things, but then compare them to each other. Like, for example, if these were my 2 graphs and I was comparing them to each other, the green one starts with more. At 0 time, it's up here at 4. Versus the blue one at 0 time is down here at -1. So I would say the green graph started with more than the blue graph did. But then with the green one, even though it starts at 4, after 1 time, it went down 2 to over here at 2. And then after another time, it goes down again, 2 more. And it'll keep going down 2 after each 1 time. So versus the blue one, even though it starts down here, it keeps going up. After 1 time, it went all the way up here to 2 because it's going up by 3. And so that after 1 more time, it's going to go up 3. So I can compare them by saying the green one starts with more. However, its growth is going down over time. And the blue one starts with less. However, over time, its growth is going up and it's gaining more. So that's like a way I can compare my key features. Another key feature that they want you to be able to compare is something called intersections, which brings us to the first vocabulary word of our lesson, which is intersect. And an intersection or an intersect, it kind of means the same thing. Like you can say their intersection is at their intersection is at blank, or you can say they intersect at blank. So intersection's the noun. It's like the thing they have, like the two graphs have an intersection spot, but also you can say they intersect at because it's a verb in this way, where it's saying what they're doing is intersecting. So they mean the same thing though. It's you call it an intersection or an intersect. But basically, this is just the big word for to cross. So to begin our notes on systems of equations by graphing, when I say the goal of a systems of equations, whenever you hear the word systems or system of equations, your whole point, your whole goal is to determine where the two equations intersect. Remember, the word intersect just means cross. So intersect is a big word to say they are crossing each other. So in this example over here, right here, this point 1, 2 is where the blue and the green line cross each other. So this is their point of intersection. So if I were trying to solve, if they gave me these two equations and they're like, solve the system of equations, the answer would be this point, 1, 2, because that's where they cross. And that's our whole goal, is to figure out where they cross. So the reason why we care about where they cross is because this means, let's pretend this was about money. So let's say the top equation was my money and the green equation was my husband's money. Well, our intersection point is that for both of us, after one, let's say X was about day. So after one day, we both have $2. And 1, 2 is a point that's on both graphs. Like for example, if I take the 3x minus 1, 3x minus 1, and instead of x, if I plugged in a 1 there, 3 times 1 is 3, minus 1 is 2. So when I plug into 1 into the first equation, I get out the answer of 2. If I take the second equation and plug a 1 into that x, I also get out 2. Because for both of them, when x is 1 on the graph, they both had a y of 2. Meaning for both of them, when I plug in 1, the answer I get is 2. So this is like a real life situation where you take two different people's equations and say, where do they cross each other? Like another example of this might be, let's say I'm tracking how much my puppy weighs. And so when I first got her, let's say the day I picked her up, 0 days, she was 1 pound. But then after 1 day, she was at 3 pounds, 1, 3. And then by 2 days, she was up to 9 pounds. And so this situation's representing my puppy. And then let's say there's a different situation that's representing my kitty. And my kitty's equation for her weight was 4.5x. So these are different types of equations, because this one's exponential, so it kind of curved up, and it will keep going up faster, the red one does. Versus the blue one's more linear, because it makes a straight line. But these two, if you were to solve the system, would have two answers, because they cross in two places. Right here, after 3.14 days, they both weigh 1.41 pounds. And then also later on, after 2 days, they were both weighing 9 pounds. So in between these two times, they weren't the same. But at these two times, they were the same. Both animals, at the same amount of time, had the same weight. So if you were asked to solve a system like this, that would be what the solutions were representing, because it was about how many days have passed and how much each pet weighed. So the solution to a system of equations tells you when both situations you're in have the same answer. So if I go back to my notes, our goal of the system of equations is to determine where the two lines intersect. And one way you can do it is by graphing. So as I was showing here, we can just put the two graphs and find where they cross. With Desmos, this is very easy. For example, if I were to scroll down to an example, 2x minus 4 and negative 2/5 x plus 8. And look, they cross right here at 5, 6, and that would be your answer. However, you're not allowed to use Desmos on this test. So you have to know how to graph these things by yourself to find the right answer. Thankfully, on the test, the only type they make you graph are linear equations that look like this, that look like the y equals mx plus b. Like they're not putting the exponentials. They're not doing the ones where the exponent is the x. Those aren't going to go on there. Neither are the other types, at least not on this test. As you do more math, you're going to have to do more systems with more types of equations. But right now, at this level, you're just doing the systems of two linear lines, where you have two linears that make straight lines, and they cross somewhere. And you have to find out where they cross. So to do that, you have to know how to graph an equation. So let's talk about how to graph a linear equation, something like 3/5 x plus 4. Let me show you the answer in Desmos quickly. This is what the graph should look like. But how do we do it by ourselves? Well, there's the slow way, and here's the slow way. The slow way is you can make a table where you can plug in x of 0, x of 1, x of 2, x of 3 maybe, and try to get some points. So if this is our equation, I can plug in 0, and the answer is 4. I could plug in 1, and the answer is 4.6. I could plug in 2, and the answer is 5.2. I could plug in 3, and the answer is 5.8. I could plug in 4, and if I plugged in 4, the answer would be 6.4. I can plug in a 5, and the answer is 7. So when I plugged in 5, I got 7. And now I have some points, so I can just connect my dots. This is the long way to do it, particularly if you're not good at multiplying fractions and adding them. Like when I plugged in 1, without a calculator, would you know that this was 4.6? Like, do you know that 3/5 times 1 plus 4 is going to be 4.6? Because if you do, then it's easy to do a table. But if you're not good at fractions in your head, then it's really hard to make a table and then graph. But there's an easier way, and here's the trick. Always works the same. No matter what number's in front, when I plug in 0, anything times 0 is 0. So 3/5 times 0 is 0. So then when you add something on, the answer is that number. See how the answer is 4? If I change this to a 5, now the answer is 5. If I change this to a 10, now the answer is 10. If I change it to -7, the answer is -7. Because anything, no matter what's in front, it could be a 4, it could be a -2. It doesn't change this from being a -7. Because no matter what number's in front, even if it's the fraction 3/5, when I times it to 0, it's going to be 0. So then the answer for 0 is always the last number. Well, if x is 0, I'm not going left or right. So I'm going to only go up to 4. So that means there's this trick that says your first dot on the y-axis is whatever this last number is. So in a general equation, if we don't know what we're growing by, this 3/5, we would call that the slope, which we use as an m. And then you put the x next to the slope, because that's what you're growing by. And then you're adding your b, and your b is your y-intercept, the amount we start with. Because at 0 time, we start with 4. So the y-intercept, the b where it crosses y, is the b in the equation. So in this case, that happens to be the 4. If I'm coming to graph it, y is always the up and down, x is the left and right. So for x at no time, I started up with 4. So that's where your first dot goes. And if we go back to Desmos, they have a dot at 0, 4. That's right there. But to get our next dot that we want, the number in front tells you what you're growing by, but it's a fraction right now. So slope and the equation is your m. However, your m, your slope, always tells you the top number is how far up you go, and the bottom number is how far to the right you go. So in this case, it means we're going to go up 3, but then right 5. So from this dot, I'm going up 1, 2, 3, but then to the right 1, 2, 3, 4, 5 to get my second dot. And then I have 2 dots, and I can connect them to make my line. And this is the fastest way to graph. If I go back to Desmos, you can see this point right here. From here, I went up 3, 1, 2, 3, over 1, 2, 3, 4, 5. And now the point is at 5, 7, because I went to the right 5. But then I went up 3 from the 4 I started at, because I started at 4. Then I had to go up 3 more, but then to the right 5 to get that point. Because what this is saying is I'm going up 3 divided by, it's taking 5 times to get there. So it took me 5 hours to go up 3 is what this is saying. So I'm going up 3 in 5 hours. So it's the up over, meaning divided by the right, how far right. So another way to write this is I could say up over right is what the slope represents. So m equals how far up divided by how far to the right for your second point. So again, I had to start at the 4, go up 3, and then over 5 in order to get my 2 points. One important thing to note is that this is only true if it's positive. If it's a negative slope, it's not going to be up. Instead, it's going to be down. Or if you want, you can change right to left, but you can only change one of them, and I'll explain that a little bit later. So here, if I'm trying to graph a system, it means I have 2, because system just means you have 2 equations you have to graph. So you have 2 you have to graph, and you have to find out where they cross to solve your system. Let's make this first one my red graph, and then I'll make the bottom one my blue graph. So for this first one, my first dot is going to be where? I'm going to go, if x is 0, 2 times 0 is just 0. And then so it's going to be minus 4. So if x is 0, so I'm not going from the middle, I'm not going to go left or right. I started with negative 4. So y is going to be down at negative 4. And then my slope right now, my m in front is a 2. Here's the thing about 2. You're going to always want to change your slope into a fraction. And 2 is the same thing as 2 divided by 1. So I have, remember the top number tells you how far up or down, and the bottom number tells you how far left or right. Since it's positive, the positive direction between up and down is up. So I'm going to go up 2, and then right 1, because right is the positive direction, for between left and right. To the right's positive, to the left is negative. However, I also could have gone down and left, because from here, if I go down to left 1 and put a dot, if you can see, it's a part of the same line. So as long if they're both positive, a positive and a positive is positive. Or if I do the negative for them both, if I do left and down, 2 negatives make it still be positive, because 2 negatives is a positive. So if you change both of them, that's fine if it's a positive too. So it's either up and right or down and left. Either both the positive direction or both the negative direction, because 2 negatives make it still be a positive too. So then from here, I could also keep going up 2 over 1, up 2 over 1, up 2 right 1, up 2 right 1. And I'm doing this to fill out the whole entire graph because it's going to be easier on me to see where they cross. And then I would try to connect them with a straight line. I'm not going to be good at this on the computer. It's not going to look straight. It didn't even go through all my points. Pretend with me. All right, let's do the blue one. The blue one starts where? The last number is a +8, which means the y-intercept when x is 0, it goes up 1, 2, 3, 4, 5, 6, 7, and then I need to add a pretend extra tick mark up there for 8. because I only have 7 tick marks. Then my slope is a negative 2/5. So with negative, I have two choices. Normally, it's up and right if it's positive. However, if I change both of them, it would still be positive. To make it negative, I can only change one. So instead of up, for example, I could go down. So from this point, instead of going up 2, I could go down 2, but then I need to make sure to go right 1, 2, 3, 4, 5 to right here. And look, you see how there's a red dot there? And it's my blue dot. So that's the dot, that's the point where they intersect. The two lines is right there. So it's this X and this Y. So if I were to count, X is 1, 2, 3, 4, 5. Y is 1, 2, 3, 4, 5, 6. The two different equations, they cross at the point where X was 5 and Y is 6. And so that's the answer. And so you would say at the bottom, to answer it in the most proper way, the two lines cross at 5, 6, because that's the point where the two lines crossed at. You can always check your work by plugging the X into both, and they should both give you out the answer of 6. So for example, I have these two equations. I graphed them, and I think they cross at 5, 6. If I want to check my work, you take both equations, like y equals 2x minus 4, and instead of x, you plug in 5. You also take the second one and do the same thing, where instead of x, you're going to plug in 5. You're saying they intersect at 5, 6, which means for both of them, when x is 5, they both should equal 6. Well, for the first one, 2 times 5 is 10. And then with the minus 4, 10 minus 4 is 6. So good. Yay. That one checks out. That is a good point for that one. Then here, if I do negative 2/5 times 5, well, the bottoms cancel, so then I'm just left with negative 2, and then I need to add 8 to that. And negative 2 plus 8 is also 6. So this one also checks out. So I know I'm right because in both my equations, when I plugged in my 5, I got the answer out of 6, which was our goal, was to find the point that's on both lines. So the first one was 2x minus 4, which again, if you look at the graph, it starts down here, it crosses y at negative 4, then it went up 2, right 1, up 2, right 1. Or you could say it went down 2 and left 1 to get that point, because it's still a positive 2 if you go down and left. So if the slope, which is your m, is positive, that means once you turn it into a fraction, if it's not already a fraction, the number on top is how far up you go. The number on bottom is how far to the right you go. But if you switch both of them, it's the same thing as going down and to the left. However, if our slope is negative, this whole up and right thing, you have to change one of them. So we can change up to down if we want. But then to keep it negative, I can't change the right. It has to stay down with right. Or if I want to leave the up, I could go left. Like I can change the right to left to make it negative. So an example of that is this one, negative 2/5 x plus 8. Is up here for the plus 8. And then you could either go down 2, but then you have to go right 5 to get that point. Or you could have gone up 2, but then you would have had gone left 5. And the reason why you wouldn't do that is because it doesn't take you closer to the blue line. So when making your choices, you're going to want to make the choice that takes you closest to the other line. So let's say there's an example that says Giselle is in search of a babysitter for her kids on Friday night. Katie says she'll watch the kids at her own house for a base rate of $20 because she's bringing them over to her house. So she's like, they're going to eat my food, use my electricity. Like, just because it's at my house, I'm going to charge you $20. However, it's also going to be $5 per an hour after that. However, Katie goes, but if I go to your house, instead, it'll only be $5 for the night, however, $10 per an hour because I have to go to your house. And so the question wants to know, how many hours would Katie have to babysit to make either option cost the exact same? So in order to do this, we have to start it with the equations. So what are the two things we don't know in this situation? Well, one of the things we don't know is how many hours Katie will watch the kids for. The other thing we don't know is how much money she is making, she being Katie, is making in total. Because we don't know how long she was there for, so we don't know how much she's making. It depends. It could change, right? The amount she makes changes based on how long she watched them. So between the two, which one's the dependent one? Which one depends on the other? Well, technically, how much she makes depends on how many hours went by. So the dependent one is how much she makes in total. Because that depends on the independent one is how many hours she watches the kids. So which one's X? Is X the hours or the amount of money in total? Remember, X is always independent in math. So X would be the hours that go by, making Y the dependent one, which is how much she makes in total. So knowing all of this now, we have to start forming our equations. Sometimes it's easier to write them in words before making the equations. So remember Y, the total amount of money she makes. So I can always start out in words by saying the total amount of money she makes is, because is means equals in math. And that's going to be true for both of them. For both of them, we can start our equation with Y equals, because Y is the total amount of money she makes, and is means equals. So Y equals, meaning the total amount of money she makes, is, for the first situation up here, it's a base rate of $20 plus 5 per an hour. So in order to make your equation in form of mx plus b, because it's easiest to graph when it's in mx plus b, you're going to want to ask yourself, m is the growth, like how much you make per an hour, because it's about hours you watch. So how much does she make per an hour in this situation? In our first situation, the red one, the slope, your growth is 5 per an hour. So I can come here, I'm going to make it red because it'll be my red situation. So she makes 5 per an hour. So the total amount of money she makes is 5 per an hour. So that means 5 times the amount of hours that go by, which is why it goes with the X. Plus, the B is just the base amount she has to pay her for babysitting. So in this situation, it's just a base rate of $20 for the night. So we add that 20 for the base rate. So she makes $5 an hour plus $20 for doing it at her house. So now if I had to graph this red equation, Well, my starting amount is 20, and then I'm going up by fives. So I can't go by ones because there's only 1, 2, 3, 4, 5, 6, 7. And I need to start at 20. If I'm going up by fives, like it's worth 5 every time, it feels good to make your scale go by fives. So your X scale can be different than your Y scale. For X, we're talking about hours. So 1 hour goes by, a second hour goes by, a third hour goes by, a fourth hour goes by, a fifth hour goes by. So we're going to want to go by ones for the X because we want to check every hour. But for my Ys, if I went by ones, I would only go up to 7. So I wouldn't have enough to go all the way up to 20, which is where I'm supposed to start. So if I want to start at 20, I could go by tens or I could go by fives. I'm going to go by fives because the slope is 5. So that means this first tick mark's worth 5. The next one's worth 10. Then 15, 20, 25, 30, 35. And if I need more, like if I don't find my 2 lines crossing before 35, I might need to go by tens instead of by fives. Like I might not have enough room, but let's try by fives. So if I'm going by fives for my red graph, I start at 20. So my first dot's at $20. And then after 1 hour, I make $5 more, so I'm up at 25. So another way to think of that is this slope is 5, and I can always divide that by 1. Because if your slope isn't a fraction, you can make it a fraction by dividing by 1. And then remember, it's up, how far up you go, divided by how far right you go. So I need to go up 5, but up 5, it doesn't mean 5 tick marks because each tick mark is worth 5. So going up 5 to 25 is going up 5, but then I need to go over 1 time. So then I need to go up 5 more to 30, which is only worth 1 tick mark, and over again, up 5 more, over again. And this is the furthest I can go without adding more ticks. So let's hope that the second situation will cross this one within this scale, but it might not. We'll find out. Now to find the second situation. It says, however, if Katie watches the kids at Giselle's house, it's going to be $5 in gas for her to drive over and $10 per an hour. So let's make this a green situation. So for the green situation, the total amount of money she makes was $10 per an hour plus the $5 for going to her house. So in our equation, what does the m become? Well, the slope is that it's 10 per an hour, so 10 times the x for the per the hour. Plus the b is what? The b is the $5 base amount for going to her house. So if I want to graph this on my graph, my starting amount is going to be at 5. So I put a dot down here at $5 for doing nothing, for just going over there. And now after 1 hour, she makes 10 more. So my slope is 10, but I can divide it by 1, which means I need to go up 10 for every time I go right 1 time. So from this 5, I need to go up 10, and up 10 would be, from 5 would be at 15. Because remember, each tick mark there is worth 5, so 5, 10 takes me to 15. And then write 1. And then I have to go up 10 again, which is 2 tick marks, and then write 1. And then I have to go up 10 again, which is 2 tick marks, and then write 1. And then this is the point where they cross. So thankfully, with my scale of by 5, on my y-axis, I was able to get them to cross. And they're crossing right here at this point, which has an x of 3. And the y amount is at 35. Therefore, the point of intersection is, if they were asking for the point of intersection, is at 3, 35. And so that goes down here, where it says, therefore, the point of intersection is. Whenever I give you a word problem, you have to respond with a word answer that makes sense in terms of the situation we're talking about. So because we're talking about her babysitting kids at her house for hours and getting money, the correct answer to the word problem is, after 3 hours, both situations will cost the same amount. So that's the solution to the system of the equations, which ask me all the way up in the beginning, how many hours would Katie have to babysit to make either option cost the same amount? And this is the answer, that after 3 hours, both situations will cost the same amount. So the interesting part of this graph is that the point of intersection is where they meet. And then after that, like if I kept going up 10 over 1 for my green one, up 10 over 1, versus the red one only going up 5 over 1, it starts to become smaller. So what I mean by that is, if I were only having her watch my kids for 1 hour, I'm going to want to choose the green graph because it's cheaper, it's less money, it would only be $15, versus if I chose the red situation, it would cost me $25 for the same hour. And then after 2 hours, still the green one's cheaper. It's only $25 versus $30 in the red situation. But after 3 hours, they cost the same. So at 3 hours, they both cost $35. Whether she watches them at my house or at her house, it doesn't matter. But then now suddenly, even though it was cheaper to do the green one, meaning she came to my house all the way until 3 hours, after that, it starts to become more expensive to do the green route. Like green ends up being worth more than red. So it kind of flip-flops. In this situation, red one's on top and green's on bottom until they cross. Then they kind of switch where the red becomes less and the green's on top of it. And so sometimes they might ask you, like, what situation should she choose? You would answer that by saying, it is cheaper to watch the kids at their own house for the first 3 hours. For the first 3 hours. Because for the first 3 hours, it's cheaper to do the green one, the one where Katie's going to the kid's house. But then at 3 hours, both situations cost $35. And then after 3 hours, it's cheaper for Katie to have the kids at her house. Because the graphs switch, where this was cheaper for a while, and then the red one becomes cheaper after that, after they intersect. The second question goes, if Giselle and you were planning on staying out for 5 hours, whose house would you have Katie watch the kids at? So then by 5 hours, 5 here, the red one is way less than the green one. So you want to pick the cheaper answer when you get a babysitter. So for 5 hours, it is cheaper for Katie to watch the kids at her own house. Because the red line was her watching them at her own house. And that's the entire lesson in short. So I'm going to be giving you linear situations specifically, where you have to fill in the y equals mx plus b part if I don't give it to you. And then you have to be able to graph it and then tell me where the two lines, the two situations cross. and tell me what that means in relation to the entire situation we're in. So now you're going to try to tell me what you learned how to do in this lesson. However, your goal is to use the vocabulary words as well as if-then statements. So, for example, to start you off, I might say, if I have two lines, then I can find where they intersect by graphing them. So here's an if, this, then something else. So that's an if-then statement where you say if this, then that. And if you know, I use the word intersect already. So now you have to also try to add in the word slope and y-intercept as well to finish explaining what you learned.